All right, now we're going to talk about spatial resolution. So spatial resolution, this is our ability to tell fine detail. So if we can see something has high resolution, then it is all about seeing everything as detailed as possible. All right, spatial resolution is kind of the easiest of the four aspects to understand, mainly because it's only affected by a couple of parameters, and only those parameters ever will affect spatial resolution. When we look at spatial resolution, what we're looking at is we're actually looking at how the actual pixels and voxels themselves, what their size is. If we have these little tiny pixels, right, the more of them we have, the sharper our image will be, because we can have more little shades of gray. So if we have the really tiny little matrix here versus a large one, we will have better detailed by using more of these blocks, all right? When we're talking about here, this is one voxel is a volume element, and that's the cube, and a pixel is the front of that cube. So the front of that cube is called a pixel, and the cube itself is called a voxel. And what's happening here is that all of the anatomy located within the voxel is averaged together to create the intensity for the pixel. So all of the, whatever you have inside of that little voxel there, whether it's bright or dark, it depends on what's inside of the voxel, and it also depends on what other parameters you chose for your contrast. What is your TR, what is your TE, what type of sequence are you running? So how we determine these pixels and how many different areas that we're going to cut this box up into is our matrix. So if we look at our matrix, we can look at a matrix of, say, 256 by 256 versus a matrix of 512 by 512. In this case, this matrix will have better resolution because we have more boxes total. So the matrix itself is when we talk about having the phase encoding going off by and the frequency encoding. Whenever we see this notation, since let's say 256 by 192, frequency always comes first, and then phase always comes second. So whenever we see this, and that's the same true when we see the field of view as well. If we were to see something that was to say that we had a 20 centimeter by 20 centimeter field of view, then that would be the field of view in the frequency direction, and then the field of view in the phase. It will always be this way for all MRI. That's the way the notation always is. So the matrix is when we look at our field of view, we look at the actual picture that we're looking at, and we take a gander at that picture. So if this was our field of view, the matrix is just how many blocks we're cutting this up into. So if this is the frequency and this is the phase, we were to have an image, say, like this, we'd have 1, 2, 3, 4, 5 boxes in the frequency direction, 1, 2, 3 in the phase. Our matrix would be 5 by 3. Obviously, usually we're dealing with, well over 200 for these numbers, but just as a quick, simple example. So when we say we're having better or worse spatial resolution, it depends on what's happening with the matrix. As this matrix, assuming that the field of view stays the same, if we had a 256 by 256 matrix, and a field of view of 20 centimeters by 20 centimeters, and we were to change that into a 5 by 12 matrix and continue to have the same field of view, then we would have this picture that we're creating. Our field of view would be the same. Sorry, I lost my first matrix. Field of view would remain 20 centimeters by 20 centimeters. But when we create more of those little boxes, more of those voxels and pixels, we end up with better spatial resolution. So out of scan number 1 here and scan number 2, we could see that with scan number 1, we are going to have worse resolution. Scan number 2, we will have finer resolution. So between the matrix and the field of view, if we were to take one voxel, let's take our one voxel here. So this is a cube containing some amount of anatomy from a patient that's going to end up becoming one color on the screen. Each pixel can only correspond to one shade of gray. So when we looked at our contrast and we looked at our different types of contrast, each pixel can only have one color. All right, every pixel can only ever have one color. So we know that we have a frequency in direction and a phase direction, right, for the field of view and matrix. And for depth, we have slice thickness. So the thickness of the slice determines the last of that dimensions within this cube. So the simplest way to go about sorry about that. The quickest way to see what your resolution is to see what is happening with this voxel. So this voxel is the size of this voxel is going to be determined by the field of view in the matrix. So how do we actually find the size of this voxel? Well, all we have to do is take our field of view and divide it by our matrix. And we have to do that in both the phase and the frequency direction. All right. So if we have an example over here where we have a 20 centimeter by 20 centimeter field of view, and our matrix is 256 by 256, and then we have a picture here of our pixel. We know that we have a frequency direction and a phase direction. And over here, this is going to be our frequency, and this is going to be our phase. So if we look at this now, we can actually sit here and calculate what the size of the actual voxel is going to be. So if we take it here, we take our 20 and we divide it by 256, then we get 0.078, and the same answer obviously is going to be over here for 0.078. This is in centimeters, which we will then convert to millimeters. So we'll just convert it down to 0.78 and 0.78. So now I know that this is in millimeters, this was in centimeters. Whenever we deal with the pixel, we always talk about in millimeters. Then whenever we deal with field of view, we talk about in centimeters. So we know that the direction here is 0.78 millimeters by 0.78 millimeters. Now let us say for a moment that we are now going to change our matrix, and we're going to continue with the same field of view. So the same field of view, 20 centimeters by 20 centimeters. But now we're going to up our matrix to 512 by 512. Now, because we have the same field of view but a smaller matrix, our box is going to be much smaller. So the question then becomes, how much smaller? Well, we can simply sit here and calculate it by taking 512 divided by 20 centimeters divided by 512 gives us 0.039. Once again, this is still in centimeters, and we're going to convert that over to millimeters by 0.039 centimeters. Once again, we're going to convert it to millimeters, and now we can see that over here we have a much smaller pixel. It's 0.39 by 0.39, this still being the frequency and this being the phase direction. Smaller pixel equals better resolution. All right, so a smaller pixel, or voxel for that matter, is better resolution. So how do we take something and figure out? We've now figured out of this pixel what the size is in the frequency and the phase. So how do we figure it out in this direction? Well, that one's much easier because it is simply the slice thickness. And that's that. So now we know, using the field of view, the slice thickness, and the voxel volume, and the matrix, we can figure out the voxel volume. Right, and that's telling us what is actually inside of that voxel. The smaller that we get it, the better that it will look. So here's an example that we put out in the text here. Is, let's say you have a 256 by 128. Once again, this looking at the notation here, we will know that this is frequency and that this is phase. Once again, frequency and phase. What is the pixel size? So we calculated it down here, and we figured out that it is 0.78 by 0.78. Now in this example, the field of view was 20 by 10 centimeters, so it was a rectangular field of view. But even though we had a rectangular field of view, because it was twice as much in the frequency direction and we had twice as many steps, we actually have very square pixels down here throughout the entire image, and we end up with numbers that appear the exact same. So when in doubt, if you cannot figure out a question that is asking you if you have better spatial resolution or you have worse spatial resolution, the first question you have to ask yourself is, does it contain the three parameters that affect spatial resolution? That being the frequency, the matrix, and of course the slice thickness. If these parameters do not change, your resolution has not changed. If the frequency, the field of view. If the field of view has gone down, but the matrix has stayed the same, you have an increase in resolution. If the matrix goes up and the field of view stays the same, you also have an increase in resolution. If the slice thickness goes up, you have a decrease in resolution. And that's how we deal with spatial resolution.